of Research in Athena Research Center, and today we're going to talk about intelligent data assistants. So nowadays we collect a lot of data from devices, from sensors, from users, from software programs, and that creates two things, two facts. The first one is actually we collect more data than we as humans can understand and process. The other fact is that we actually have the situation where more users and more types and groups of users want to have access to data. Take an example, health data. You have, for example, health records, and you have biologists that want to have access in order to get information about insights, patterns, and so forth. You have doctors that want to have access to the medical records of their patients to seek information inside these records, find past symptoms and past drugs, and so forth. And you have the patients themselves that they also want to have access to their data to be able to find what was happening to them 1 year ago, how was their health symptoms progressed over the years, and so forth. So the problem we are actually facing today is not how we can collect more data. The problems we are facing today is how can we actually explore and leverage the data that we have in easy and intuitive and meaningful ways for most people. So a database person would say, hold on, this is a piece of cake. You have a data store, name your favorite data store here, Oracle, Redis, whatever you want. And it can understand, for example, queries in SQL. So if you write your query in SQL, it will return back the results you hopefully want to, and that is pretty easy. So for example, here I have a query in SQL that says select p.status from conference attendees P, where p.conference equals to Spark AI 2019. This is not what I want to ask really. What I'm really asking is this. So I would rather have an interface, a system that allows me to explore my data in ways that I understand, not in ways that a developer or SQL programmer or a data scientist is able to understand. So we are talking about data exploration, and essentially we have two phases. We don't want to go very back in history. So we have the the SQL age, where essentially you have the system that understands SQLs or whatever programming language you want to have there. And you have the programmer that knows very well how to program over the data, that understands the data domain, the schema of the data, what the database looks like, and whatever you tell him, he will be able to find the right thing to write, to code, and get back the results that you want. And then you have all these poor people over there on the left side of the slide who are actually the people that care and want to use the data. It's not the programmer that wants to access data. It is a doctor, it is a patient, it is a biologist, not the programmer. He doesn't really care. We don't really care, honestly. So all these people are actually depending on the developer, either explicitly or implicitly. Explicitly because they want to access in the data, so they have to go and ask the developer to get their data for them, the answers they seek, or implicitly because the programmer has written some tool, some search interface, and they will use this search interface. So essentially what we see in many organizations is what we call data starvation, because the people that really need to have immediate access to the data and get answers from that, they're actually isolated behind the programmers or tools that are not fit for these users. And nowadays we're actually in the baby talk age, where we see these tools that start to emerge. They have actually started to emerge the last few years that allow people to speak in some form of natural language and ask the queries they want in this form rather than some programming language. So essentially what we have here is, for example, a business user who is a domain expert essentially. So he knows about the data, he knows what he looks for, and the interface allows queries that are rather easy to understand. They don't have high levels of ambiguity. They usually support some template approach that expects specific types of queries. So things are nice, but very simple. And then we have chatbots. So a chatbot essentially is a tool that mimics conversation with people. They use artificial intelligence techniques. We meet them in consumer platforms for consumers and brands to talk to each other. And actually, this is where things start to get interesting, because this is how we would like to talk with our data. Having a chatbot that understands all the kind of queries we ask, that helps us find what we seek, and so forth. Well, chatbots are not there yet because they are a rather simple programs that are based on some linear conversation paradigm, and they can support specific tasks. So you can order a pizza, and you can also find a cinema to go tonight, but you cannot ask any type of query on top of any type of data. And you have, of course, more advanced tools, such as Google Duplex, which is trained in using deep learning techniques in closed domains, and it can support more natural conversations, but that is still away from where we want to be. So what we actually want, we want to have human-like data exploration for any type of user to be able to ask queries on any type of data without making any assumptions that this user actually is a developer. He is not a developer. He is the user and the consumer of the data. And the system we are talking about, the intelligent data assistant, should be able to converse with the user in a natural experience. And it should be able to guide the user when the user doesn't know what to do next, giving explanations, giving recommendations. It should keep track of the context and adapt. And of course, the intelligent data assistant collects data itself, so it should use this data to learn and evolve over time. So what we're going to talk in the rest of the talk is about 4 main components of our intelligent data assistant, and see how they operate. So the top two are about how the assistant understands queries in natural language. The third one is how the assistant converses back using natural language itself. And the last one is about how the assistant can help the user navigate during their data exploration trip and find what they are looking for. So let's start with query understanding, how we enable the user to ask queries in natural language. And let's start with a fact first. When people use search engines, they're expecting to give simple queries and expect maybe not very perfect results. But when we go to data repositories, users want to ask very sophisticated queries, and they expect, well, rather perfect results. So this puts the barrier very high, and on top of that, translating a natural language query is really hard. So some of the challenges that we have come from, of course, from the natural language side of the things. So you have different words meaning the same thing, movies and films. You have the same word meaning different things. So Paris may be a person, maybe a city. How do you figure this out? You have syntactic challenges. The same sentence can have multiple readings based on the syntax. So you say, find me all German movie directors, and this can be read in 2 ways. You want directors that have directed German movies, or you want directors from Germany that have directed some movie. Both are okay, but what does the user really mean? And of course, you have semantic interpretations of the query. When you say, are Brad Pitt and Angelina Jolie married, what do you mean? Married to each other or to some other person? And more challenges. For example, when you say, return me the top product, the word top means something different depending on your domain, depending on the context of the query. So things get even more difficult. And then you have queries that are missing important information. A very simple example. When you say return the movies of Clooney, who is Clooney? Is it a director? Is it an actor? Or is it the producer Clooney? And this is just a very simple example of how things can get difficult. But the data itself poses many challenges. First of all, SQL, since we're talking about SQL, let's keep playing with SQL, has a very strict syntax. So maybe you say something in natural language that is pretty simple, But when you try to translate it, to map it to the actual query SQL that needs to be executed, this is very complicated. So for example, when you say, give me the movie with the best rating, maybe in your mind you would expect that the SQL query would look something like select name, maximum rating from movie. Well, it's not. And then you have the database structure. You're asking about date, but the system knows about years, months, and days. So how do you map from one thing to another? And of course, you have multiple relationships. For example, when you say, give me Woody Allen movies, you expect Woody Allen movies, but the system actually needs to go and fetch information potentially from many different tables and join them and bring back what you are looking for. You don't care, but the system cares, and that is difficult for it. So let's start with a query that says, find what movies have the same director as this movie here, Revolutionary Road. And the first approach that we are doing is actually trying to understand the query linguistically. So you use a syntactic parser, for example, the Stanford parser as we are using, and you try to build a dependency parse tree that gives to each word in your query an annotation that depicts the syntactic function of this word, plus you find the syntactic relationships between the words, so how each word relates to each other. And then you try to map the information that you have in your data. What are the tables, the attributes, and the values that are mentioned in this query? And then once you have this annotated query, annotated parse tree, you try actually to map it to a query graph that represents a possible query over your data. Once you have that, then it is pretty easy to actually build the actual code to execute over your data. Now let's see an example. So we start with a query that we already saw, and the syntactic parser would give us a tree like that. It is simplified, but just to give you an idea of what the syntactic parse tree would look like. And then we take this and we try to find, for example, that Revolutionary Road is actually a title for a movie, and movies is actually refers to the relation movie in our data, and so forth. And then we try to take this tree and map it to a graph that represents a possible query. And now here this graph tells us how the various nodes, the various components must be related to each other over the data in order to bring back the answer that we want. And the final query looks like this. So this is actually a good example, even if it is a simple example actually, but it's a good example to see that we wanted to execute a query that is very simple if expressed in natural language, but it is already a little complicated for an ordinary user to come up with. So that is why we don't want to go there, and we prefer this path. So understanding syntax is difficult for people. It is even more difficult for automated programs such as parsers. And the reason for that is that there may be many different translations for the same thing, and the parser needs to come up with, to pick one. And the choice of the parser may not be the best, and that will actually halt or block the whole process. So what do? The second approach that we use at the same time, complementary with the first one, is actually to let the data tell us how we should translate a natural language query. So the first path was let the natural language query drive us. Now we let the data drive us to the same end. So here is a different query. Very simple, right? Show me Italian restaurants. Well, the parsers here cannot really help us because the query is so simple that, but that's not the problem. The problem is, and here we have an instance from the Yelp database for this example. So you have businesses that have hours and attributes and have different categories. And the problem is that Italian maps to many different attributes. So you have Italian in the category, but also Italian as part of the business address. Same with the restaurant. It can be actually found in many different places. And if you combine all these attributes in different attribute combinations, then you have many possible query interpretations. Some of them may be more likely than others. For example, a business categorized as restaurant and as Italian sounds good, right? And same with a business categorized as restaurant that serves Italian. That also sounds good, and actually, the two of them may bring complementary results, so you want them both. But there are also other interpretations that probably you don't want to see the answers. For example, a business whose address contained restaurant Italian, yes, it actually exists in the data, but probably the user is not asking for that. So how do you tell which interpretations are actually more likely than the others? So here is an overview of the data-based approach that has the following components. So we have the entity mapper, where the idea is, again, that we try to find which parts of the query actually exist in the data. And we have the interpretation generator that tries to find different interpretations. But the key component here is actually the machine learning-based disambiguation component that works together with the entity mapper and together with the interpretation generator. With the entity mapper, it tries to figure out which of the mappings are actually valid, good mappings, useful. Similarly, with the interpretation generator, it tries to figure out which interpretations are more likely and which are not. In order to do that, we use two sources of information. We start with expert data when we don't have any other source of information for our data. When the data starts, when the system is in use, then we start collecting query logs. And we can actually use the query log information to see how we should disambiguate new queries based on how we disambiguated and users responded positively past queries. Now here, for the machine learning-based component, we are using different techniques for that. So we're actually using typical, let's say, machine learning, but also deep learning techniques. I would like to give an example, actually, of the machine learning-based technique, because it is simple and actually works pretty well. So the good news is that we can use classifiers that use as features statistical components, statistical features on top of the data. For example, probabilities that show how common an attribute mapping is, or the exclusivity of a keyword inside an attribute that tells us whether this word is something interesting within this attribute or it's not very interesting, so maybe you shouldn't take it into account. Similarly, with the attribute combinations, we can also rely on statistical features. And the good news with that, so one example here is again probability, and another one is an information retrieval-based relevance score that computes for each attribute combination the score for each initial attribute that is within this combination, and then a total score over the whole attributes. The good news is that we can compute these statistical features very easily, very fast, and we can have pretty good accuracy. Now, moving forward, how does the system respond in natural language? So you have the user that is asking for comedies by Woody Allen, and the system actually understands this query or that query. But it cannot show either of these to the user because it beats the purpose of having an intelligent data system. So we would rather want to say something like this. So the system should ask, do you mean the director or the producer, Woody Allen? And then the user can reply director. And in this way, we build a conversation between the system and the user that can help the user go to the right direction and find what he's looking for. So how do we do this? So first of all, we take the query that we have, which is now a structured query because we have already analyzed the natural language query and we know what is the SQL query that we have. And we take a graph that the query graph representation for this query that we annotate with two types of information. Annotations such as relation actor is translated as actors, and templates that tell us how we build sentences on top of a query graph. Okay? So an example template here says that if you are on a query graph and you have two nodes, you can build a sentence that has some expression, the label, the annotation of the node, you, some other expression, the annotation of the other node, and so forth. And then in order to build an actual sentence, we do a template-based approach that essentially traverses the query graph using a domain-independent technique and builds sentences using the templates and the annotations. But it's much easier if we see a very simple example. So this is a very simplified query graph that actually represents the query select actor name from actors, movie, and cast, where you join all the tables, and year is equal to 2010. So here we have, does it work? So here we have a template that tells us how we should read this part here, and another template here that tells us how we should read the other part. And the sentence that we come up with looks like this, more or less. Return the name of the actors for actors that play in movies in 2010. But we can do much better than that when we start having users in the system, because then we, apart from the annotations and templates that these are expert given, we have the logs from translating natural language queries to SQL queries. And this actually provides us with a lot of useful information to come up with explanations that are more natural and closer, if you want, to what the user would say if he was asked to give the same explanation. Now, the last part is how we can help the user ask the right question. So essentially, most of the times what our users are telling us is that when they are sitting in front of their computer, they think they're sitting behind a wall. And behind the wall is where the data lies, and they don't know how to access the data. And they face this problem at every stage, if you like, of their work. Even if they start with a new data set, so they don't know, okay, what type of question should I ask here? But also when they actually working with a data set, they need help often to find what they should do next, what type of question they should do next, how they proceed with their task. So essentially here, we see in the query recommendations, we see two settings. One setting is what we call in recommendations a cold start, where essentially we start with a user that has no previous interaction with a specific data set. And we want to be able to provide to this user a set of queries that would help him or her understand or get an idea, if you like, of how the data look like, what type of queries are possible, and start from somewhere. And this is vital. Now, in the warm start, on the other hand, we have the user that's actually exploring the data set, asking queries and going on. But then we always want to help the user. So it is the same paradigm here as you have in a Google search, where you search for something and then Google at the same time offers you different types of recommendations, related queries, queries that other people asked, things like that. All these help you see different possible ways you could ask the data, and they are very helpful tools. So in the cold start scenario, essentially, the starter query generation starts with data statistics that essentially tell us which part of the data may be more interesting or more important than other parts, which tables, which attributes, which values. So here we have a lot of different statistics that essentially create a repository that is very meaningful and very vital, but also gives us a lot of different options that we need to sort out through. We may have example queries, and example queries come when we're dealing with data sets that may be similar with other data sets. Okay, so example queries there can help us transfer some knowledge from one data set to the other. And of course, if we have user logs, then we can also use information from the user logs. The first observation here is that we use everything that we have in our disposal, because all these different pieces of information tell us different things, and we try to make the best choice. The other important thing here is actually the metrics that we are using. The metrics that tells us two things. The first thing is whether one individual query is important, useful, representative. There are different things here, different aspects that need to be considered. And the second thing that they tell us is whether a set of queries in total is useful for this particular user, for this particular data set. Now, when we go to the warm start scenario, we have two approaches here that work at the same time. The generative approach essentially works on the query that the user has currently submitted and performs structural modifications of this query, again, based on data statistics. So if you're asking for this, maybe you want to add this selection condition and ask this next query. The interesting part is also the log-based approach, where essentially here we are actually mining the query logs that we have, and we build two graphs, a transition probability graph and a query similarity graph, each one giving us a different path to recommend queries. So essentially with the transitional graph, we're able to recommend queries that follow the current user query in our user log. So essentially here we say that usually people, when they ask this, then they want to ask that. Query similarities, on the other hand, do not follow this logic, but they try to find queries that look similar. These queries, they do not necessarily live close together in the user log. They just show similarities in their content. All this give us a set of different sets of queries that we show to the user as different options to explore the data. Now, putting everything together, on one hand, we have the four components that I described today. On the other hand, on the right side, we have not only the data that we are dealing with, but we have lots of data that we actually generate. We have knowledge bases that tell us, for example, that movies and films are the same thing. Depending on the domain, we want to use different knowledge bases, by the way. We have template and annotation bases that tells us how we can comprehend the data we have and how we can build natural language utterances on top of our data. We have, of course, the query logs and our translation logs. We have graphs that capture query similarities and query translation graphs. And between them, we have a very big data processing pipeline, or pipelines to be more precise, that allow me to use this term, lives very happily on top of Spark, using Spark SQL, Core NLP, MLlib. Lately, we start to use TensorFlow for our deep learning component that has to do with how we disambiguate queries that have a high level of disambiguation. We use GraphX, of course, because it allows us very nicely to build and keep updating our graphs on real time. And this is actually very nice. And Spark MLlib, I think I already mentioned. So with that, I would like to say that intelligent data assistance is, or call it whatever you like, is what we think is the future for how we should explore data. Our users and customers come from 3 different domains: health data, not movie data, not the movie industry, health data, biologists, and astronomers. They all are users with high expectations as far as their data is concerned, but they really do not want to work with with data scientists and developers, to be honest. They want to be able to access their data and see information there, at least to a point that they can understand. And then they can potentially go and talk with the data scientists to find more insights or more patterns. The second observation is that this is essentially work that has a lot of challenges. We are still not where we want to be as a community, not as an individual project, but I think it's really interesting, and I would like to thank you for your attention so far.
We've got about 10 minutes for questions. If you just raise your hand, we'll bring the mic around and we can take some questions from the room.
Do you have specific cases you have worked with that we can understand or relate to?
Yes, one specific case is health data. We are working with doctors and hospitals that have big repositories of medical records, and they want to be able to find information inside these records at two levels. At the level of, for example, a doctor needs to find information across different medical records by just asking queries in an easy way, but also at the level of scientists, biologists that work that are part of the team of the hospitals that want to be able to perform in an easy way machine learning and data mining tasks, but they want to be able not to program them if they do not need to. They want to be able to program, if you allow me the expression, the whole thing in an easier, more free-form-like style. So this is one of the most challenging domains, health data, because it is easy when we talk with examples with using movies and the Yelp reviews and Yelp businesses. It is easy for us to understand what is going on. When we go to health data, they have a lot of different types of data that need to be brought together. As an example, just the DNA sequences, if you start if you want to bring them in as part of your queries, they multiply the challenges that you have because they bring ambiguity and they bring multiple different facets themselves. So this is one domain. And the other one is we are working with actually Max Planck Institute and the astronomy department of Max Planck Institute to allow the astronomers there to be able to ask queries in natural language. And this is actually also a very interesting and big domain, totally different from health, but very interesting as well.
Thank you for an interesting talk. Does this also work in non-English languages? In non-English languages, like Dutch, for instance?
That's a very good question, and that is a question that holds for all these types of queries. At this moment, the natural language part, some part would work in Dutch, some other part would not work in Dutch. Which part would not work in Dutch? It would not work the syntactic parser because we are using Stanford right now. Things like query recommendations and natural language explanations, this would work immediately because you need to, if you give the expert database in the system, it can be anything, it doesn't care. So the answer is some part of it would work immediately, some other part would need some changes.
Okay, thank you.
Thank you for your talk, it's really interesting. So my question was this solution or this toolkit, is it like something that can be productized, or is it something that you're configuring and training for the individual use cases that you spoke about before? And if it can be productized, then is there any code or any plan to release this as a SaaS or something like that?
That's a very good question. And so on one part, there are challenges that are domain specific, and this is something that I want to stress as much as possible. On the other part, however, the algorithms that we are building are as much domain independent as possible because it doesn't make sense to have something that works on this one, but you have to rebuild it if you want to make it work on something else. The unifying glue here for the systems that we have so far is Spark. It really made a big difference, and I would like to have one talk just to talk about how much difference it made. And to answer the last part of your question, yes, the plan is to productize it. we are trying to work with these two different user groups, 3 different user groups, because we need to do this right now. But the plan is through this process to actually go to productization. Thanks.
Hello?
Yeah.
Hi. I was just wondering, what's the interface then for when you make your program? What's the interface for doctors or the physicists when they want to query the databases? Is it an app? Is it a
It is an
program?
app.
Okay.
It is an app. But that doesn't, so the app that we provide, which maybe you may go with a different app, allows natural language, allows visualization, so it builds everything on top of that. But you may also want to use something else. There is no, there's no restriction on which interface you will use on top of that. The API we provide allows you to build whatever you want on top of that.
Hi. In my experience, when looking at sort of large data sets that come from possibly disparate sources, it's sometimes hard to get the correct answer to your query without understanding the data. And as a layperson attempting to do this without understanding that data, you may get a result that looks correct, but perhaps isn't. And as you base your algorithm also on the actual query logs of users, it may appear that, say, the query was the intended one, when reality is not. Is there any attempt to address this or solve this?
This is a very good point. It is one of the big challenges that tell us why we have not solved, so we don't have the chatbots for data exploration yet. In order to address this, that is why we're using multiple different approaches. And I try to illustrate 2 of them. So we go through a syntax-based approach, a linguistic approach that tells us linguistically how we understand the query. We also go through the data, because the data also tells a different story. And that's why there we're using machine learning-based techniques. You give me a very good base to say something on deep learning that I wanted to say, actually. During the talk, I talked about simple machine learning models that work pretty well for disambiguation. The last couple of years and half a year maybe, there is a lot of work in deep learning models that try to map natural language queries to SQL or some type of query language. And so we are experimenting with this. It is interesting because all the problems that you mentioned, they actually appear in the deep learning domain. So I think the answer would be using a hybrid model, as we do right now, using some not machine learning model, if you like, but also let the data tells us what we want. So I'm not sure if I answered your query or your question, or I rather took the opportunity to say something that I wanted. So you can ask again. Okay.
Any other questions? One at the back.
You will be very fit by the end of a Spark conference.
Hi. The user expects a fast results from database, or how do you handle a case that you can run timeout or stuff like that?
How do you handle cases that?
The timeouts.
What timeouts? What times out?
So if a user cannot expect a result in 20 minutes, he expects a result in real time.
It depends on what the user is asking. So if the user is asking something simple that the expected answer is you need to give the answer yesterday, yes, you should, you should give the answer yesterday. There is no way you can actually avoid that. But there are also other cases where, for example, the first question that came from the audience was if we have queries that have machine learning. So when you have a scientist that says, give me that, and that also requires a machine learning thing to happen, then the response time may be different. So it depends on the user that you have and what type of queries you have. So the timeout, you need to tell me exactly what you mean by timeout here.
Okay. So I was wondering if the client used this system as like a relational database, and the system is slow. It can be very slow. The complexity of a query can be very big, and the answer can be very slow. So I just trying to understand what you are doing in those cases.
If the answer is very so, maybe we should distinguish two parts. The one part is whether if the user was asking the same thing in, let's say, SQL, okay, and the user now is asking the same thing in natural language. Hey, that is great, but does it take more time? So that because the system needs to understand, to figure out. So is this what you mean?
Yeah.
Yeah. No, that's what. No, it doesn't take more time. That's why that is one of the big advantages going over Spark, that let us reuse and bring information in front of the user very quickly. But we have to build all these type of things that we need in the backend in order to make this work fast.
Okay, makes sense. Thank you.
Okay.
We're out of time, so if there's any more questions, please take it up with the presenter at the front of the stage. Before everybody disappears, just a reminder, please rate and review the sessions, and a big round of applause to our presenter, please.